Okay, yes, let's get the show on the road. All right. Hello, everyone. Hope you're well. Welcome to another edition of Math 1206. Let us jump into it. As usual, we were in the middle of a topic last time, and I left you guys some stuff to do. Share screen. Maybe I didn't tap the button. Okay, there we go. All right, so we have, let me maybe recap a little bit. What did we do yesterday? Yesterday, introduced a new differentiation technique. So this was called log differentiation, and it's when we use logarithms to help us out with differentiation, because logarithms have a lot of nice properties. They turn powers into multiples, they turn products into sums, they turn divisions into subtractions. So it makes sense that if I have something weird to differentiate and the power is an issue, I can use a logarithm to help me out. So I already know how to deal with x to a constant power. The fact that this was x to a variable power makes it complicated. It doesn't fit either of the rules that we had that had exponentials in it. So we know how to deal with x to a constant power. We also know how to deal with a constant to x power. And by the chain rule, we know how to deal with a constant to any variable power in theory. But a variable to a variable power, kind of strange. So what we can do is we can set some variable equal to that function. We can log both sides. We can simplify, and then we can perform implicit differentiation to solve for the derivative. And I wrote out the steps here. And I also mentioned that log differentiation, it's useful in these two situations. If you have a complicated power, or sometimes if you just have a complicated expression where doing the product rule and quotient rule and or all that stuff would be really annoying, like this one, right? Like here you'd have to do the quotient rule. Within the quotient rule, you're doing a product rule. Within a product rule, you're doing the chain rule. Super annoying. However, by logging it, it breaks down into a lot of very simple pieces, which harkens back to a long time ago when I mentioned when you want to do calculus stuff, you want to expand logs as opposed to keep them contained in one big log. We had the alternative here, a way that we can get a log in there without having to go separately and set y equals to the thing that we care about. We can just rewrite that thing as e to the ln of that thing. And it accomplishes the same thing, except we now have like the log of the thing that we care about in the power of an exponential, which we had to implicitly we had to deal with anyway. All right, so that was log differentiation. And next thing we did was indeterminate forms. There were 7 of them. 2 of them are convenient to us, 0 over 0, infinity over infinity. But these are some other ones. It's indeterminate if you cannot determine, it's a limit form that cannot be determined at face value, which means you have like these competing ideas that kind of don't agree with each other. So like 0 to the 0. If the base is 0, it should be 0. And if the power is 0, it should be 1. Contradiction, right? Base is infinity, should be infinity, but power to 0 should be 1. Base is 1 should be 1, but power to the infinity should be infinity. 0 times infinity. 0 times anything should be 0, but then you have this idea that infinity times anything should be infinity. Infinity minus infinity is also weird because the infinities can be at different sizes. Different functions can approach infinity a lot quicker than others. 0 over 0 because, of course, division by 0, but also because any fraction where the numerator hits 0, parentheses, the denominator is not 0 at the same time, that fraction will hit 0. So also, again, infinity over infinity, because infinities can be different sizes. However, the 2 of these forms are convenient for us because they allow us to use something called L'Hopital's rule, which pretty much tells us that if you have a limit form that is a fraction and it approaches 0 over 0 or infinity over infinity, then the original limit of f over g is going to be the limit of f prime over g prime. So you just differentiate the top, differentiate the bottom. And as I mentioned, only in these conditions, which is why I boxed that in red. You can't just do that anytime. You can't. You also cannot take a limit just by differentiating the limit. That is not what this is saying. So if you have the limit of a rational expression and it approaches 0 over 0 or infinity over infinity, then you can compute that limit by taking the derivative of the top, derivative of the bottom, and you still have to take the limit. And if the second limit exists, it will be the same answer as the first one. You can do this multiple times, but as I mentioned, you want to simplify each time because you do have situations where you can go into like this infinite loop of just keep taking derivatives forever and you never actually get anywhere. Forgot which one. I actually saw an example like that. Yeah, like this one. Technically, you could keep applying L'Hopital's rule like forever, and you would never actually get to a point where you can evaluate it. But at this step, because we simplified, we can now escape the loop. So you are going to want to simplify each time you apply L'Hopital's rule. And we did a bunch of those. We did a bunch of limits. We did a bunch of situations you can be in where you're not exactly in L'Hopital's rule, but I showed you how to put it in a form where you can use L'Hopital's rule. So if you have one of the other indeterminate forms, if you have one of these other guys, the 5 guys on the left, you can know how to do it. So if you have something to a power, so the first 3, the trick is to get the log in there. So you can log both sides or rewrite it as e to the ln of blah. For 0 times infinity, the idea is to take one factor, move it underneath, take the reciprocal. For infinity minus infinity, factor, check if you can do it. If not, take one factor, move it under the denominator, and you can see if L'Hopital's rule will help you out there. We did also derivatives of inverses. I think that's the next thing that we did. Yeah, derivatives of inverse functions. So I didn't really review inverse functions. I assume you guys will know about the basics of those, but I reminded you of the important properties, kind of like inverse functions cancel each other out. Using that fact as well as the chain rule, we were able to figure out that the derivative of an inverse function, if we wanted the derivative of f inverse of something, that's a formula that we can use to get it. Using that formula, we derive the derivative of tangent inverse. We derive sine inverse first, which the derivative of sine inverse of x is 1 over 1 minus the x squared. That's a chain rule version. We also derive the derivative of tan inverse of x, which is 1 over 1 plus x squared. And I just gave you these as an FYI. I don't expect you to memorize these. I'm not going to ask you about any of the other inverse trig function derivatives directly. I don't know. If the mood strikes, I might ask you to derive one of these formulas using what we've learned, but you're not going to have to like have them memorized. And even that, I probably would put in like the bonus section of it, a test or something. Not guaranteed. Like I could just as well not do it. Not married to the idea. And the laptop here was spatting out. Anyway, yeah. So that was just an FYI. But now I have some more examples left for you guys to do. And so that's what we're going to do. That's where we are right now. So we want to do these. Let's get to it. Okay. Let's create some space here. We probably wouldn't need that much space, but it's hard to tell in this fake paper. This one probably needs more space. I don't know why it's doing that. Actually, I think I know why it's doing that. Okay, so yeah. All right, let's go. Let me make sure that that is cool. Sorry, I just want to get some nice formatting here. And sometimes it's kind of annoying to do that on the iPad. Yep, the iPad messed up that thing. Oh, geez, amount of time I spent doing this, you guys could have done all the problems already. So what'd you guys get for this one? Ideas? Do you remember what the derivative of sine inverse is? No one's alive out there. Let me remind you, the derivative of sine inverse is 1 over the radical 1 minus x squared. And the derivative of tan inverse is 1 over 1 plus x squared. Okay, so now do we know what to do? How would we apply that rule? What would we get? Do we not know, or are we working it out, or what's going on? Okay. So this implies chain rule version. So here it's like, that's your U. Is U prime divided by the radical 1 minus U squared. That could be simplified, I guess. I wouldn't care too much. Here, chain rule version is, of course, that. So you can kind of one-shot this one as well. Leave the constant alone, take the derivative of the inside, divide by 1 plus inside squared. And that. For this one, of course, you'll need a product rule here. So we're going to differentiate the first one, leave the second. Plus leave the first, differentiate the second. I mean, that's nothing else we can really do here. So that'll be that one. Okay, so in this one, we have our x's and y's kind of mixed up together. We even have a y stuck inside of a sine inverse here, which we can't get out. So we need implicit differentiation here. So it's u prime over the radical of 1 minus u squared. U prime, you have to differentiate x plus y. So that's 1 plus y prime over the radical of 1 minus u squared. Derivative of y is y prime, derivative of x is x squared is 2x. So we have our y prime here that we need to solve for. I would break it into two fractions. Then we have y prime on this side with that. And we have 2x minus this. This guy we can simplify a little bit by multiplying and dividing by that. So we have 2x times the radical of 1 minus. We have that. So I don't know, but I'm guessing you guys tried that and got that. So unless you guys tell me otherwise, I'm just going to assume that. Yeah. By the way, has anyone checked out that tutoring thing that I mentioned? I sent out a flyer about tutoring a couple weeks ago, maybe a week ago and change. Was it last week? I don't remember. I sent out a flyer. As soon as I got it, I sent it to you guys about tutoring for the summer. I don't know. Did anyone actually check that out or? You're not sure? Okay, so here's one. You're given a function and you want to find the derivative of f inverse. Now, can we do this? For this particular function, I don't think we would need the formulas that I gave you, but it would be very annoying not to use them. There are other functions where you wouldn't be able to do it any other way. So I'm going to do it the way that would work more generally. Because you could say you want to find the inverse function first, and then take the derivative and plug in 2, which would be very difficult, or at least find it at 2. Would you be able to do that here? Be very ugly. Maybe not. I know at 2 it would work. Because if that is equal to 2, you bring it over, you can factor stuff, factor by grouping and simplify it. But let's actually try. So we know that the derivative of the inverse function is 1 over the derivative of the original function evaluated at the output of the inverse function. And so that would mean the derivative of the inverse evaluated at 2 is going to be that. So now what you need is you need to find both of these. You need to find f prime, so you can plug in f inverse of 2 into that formula. And you also need to find f inverse of 2. So here we need f prime and f inverse of 2. Now f prime is not that bad. So this guy, 5x to the 4th minus 3x squared plus 2. That was x cubed. So that's not bad. So that's the first one. Now, the second thing you have to find is f inverse of 2. Okay. And this is the function. So maybe I can write that down here. So that's our function. Anyone knows how you would go about finding f inverse of 2? Like if you had to find f inverse of 2, what does that mean? How would you do it? Anyone? Bueller? No. So, right. So this was something we spoke about yesterday, which I think you were absent for. The notation -1, when you put like -1 on a function like this, it does not mean like 1 over. It means something else. It means the inverse function. So let me put it this way. Right, you have a function, you have a domain, and you have a codomain. A function is just a rule that takes guys from over here and gives you exactly one output over there, right? And a function is just the rule that tells you how to do that. So some functions, not all of them, only the bijective ones, will have what's called an inverse function. And what the inverse function does is it undoes the original function. So over here, if you have x, f is going to output f of x. And the inverse function takes that as input and it outputs back the x. So f inverse of f of x is going to give you back the original input. The function just undoes what you want it to do. And it's not always a reciprocal. So it's like if I had y equals, I don't know, 2x plus 1. So there's a function that say it will take 1 and it would give you 3, right? How do you go from 3 back to 1 by reversing this rule? Right? It wouldn't be 1 over, because 1 over would just give you a third. Or so it's not that. You have to find the function that takes your output as input. And so when we say f of x equals y, it's the same as saying x equals f inverse of y. We also spoke about that yesterday. I don't know if you got to watch the video yet. And so if you take f inverse of the output, it gives you back the original input. So going back to this function, say 2x plus 1, just for an easy example, if I had y equals 2x plus 1, f inverse. To find the inverse, you might remember this from pre-calc. You switch x and y and you solve for y. So that's like you switch the input and output, and then you just turn the function around. So in this case, you would have x is equal to 2y plus 1. This means that you get x minus 1 equals 2y, which means that your y would be x minus 1 over 2. And you'd realize that anything this original function does, this would be f inverse. And you realize that anything this function does is going to be undone by this function. And you can check that. So if you were to say f inverse of f of x, that means you're going to plug in f of x into the inverse function. Plugging in f of x is 2x plus 1. So you'd plug in 2x plus 1 minus 1 all over 2. The ones would kill each other. You would get 2x over 2. The x's would cancel, and then you would get x. Right? So you get back the original input. So it's not just a 1 over function, it's a whole other function. Now, in this case, I could solve for this function relatively easy because it was just a linear function, mx plus b, right? It's easy to solve for the other guy. If this function were more complicated, though, like this guy, this guy, it becomes a lot harder right away. So if I were to set this equal to y, how would you switch x and y and solve for y? How would you solve for the x in this? It's a 5th degree polynomial. There's no general formula for it. You'd have to kind of get lucky. And I don't think this is one of the ones where you can get lucky with. However, in this case, we were not told to find the inverse function in general, just the inverse function at a specific value, f inverse of 2. So that becomes easier. What you really want to do is set this equal to 2 and solve for x. And it turns out that's a little bit more manageable. That even a pre-calc student could do it. But a lot of times in this class, you're going to want to do it by what we call by inspection. And by inspection really just means you eyeball it and see the answer, which I know it doesn't sound like a method, but that's actually the method. There are times when you're going to be given the function that you can't solve for the other guy. You won't be able to flip it. So yeah, that's just a little some side notes there. Yeah, so when you say f inverse, the -1 power, it's a notational thing. It does not mean 1 over. 1 over would be if it was on the outside. So if it were like that is this. If you write this, it's not that, right? It matters where the -1 is positioned. right? So there are little things like that. And this is why, just to kind of throw it back, I mentioned in the first class about how super important it is to pay attention to notation. Like I didn't just say that to be a stickler. I really mean, like, you can get the complete misinterpretation of what's going on just by not understanding what it means for a number to be in this position as opposed to that position. And you can completely get everything wrong. So you have to be careful with notation. Now, to be fair, the inverse notation actually does come from the fact that you could divide, because if you have y equals x is your f of x, it turns out that your f inverse in this specific case would just be 1 over x. And so that happens to be x to the minus 1. And so they're like, oh, let's just make it like a minus 1. The inverse is like a reciprocal kind of thing. But I don't know. When they were making up this notation, they didn't think too far ahead, I think. So, because it's not always the reciprocal. It's only the reciprocal in very few cases. You could solve for when it's the reciprocal. I think only x would be the reciprocal. Anyway, but you could solve for that. Okay, so that's just a little crash course in inverse functions. So it's not just 1 over. Like, there's a whole other rule. The point is to reverse the rule, and you don't necessarily reverse any rule by just putting 1 over. So again, just based on what we were saying about inverse functions yesterday, if you want to solve for f inverse of 2, you don't know what it is, so you set it equal to some unknown, set it equal to x. But that would mean, of course, that 2 is equal to f of x. And that would mean that 2 is equal to x to the 5th minus x cubed plus 2x. Now, we could actually solve this, but I don't want you to solve it. What I want you to do, because this is going to be good practice for the future, and you'll see some of this in your homework as well, is solve it by inspection. Now, by inspection is just a fancy way of saying, like I said, we just kind of eyeballed it and we know the answer. So can anyone see what x would have to be to make this true? Just kind of eyeballing it. Right, x equals 1, exactly. So you just did the problem by inspection, right? You didn't have to go, oh, move the 2 over, factor by grouping, because you could have done that, right? You could have been like x to the 5th minus x cubed plus 2x minus 2 equals 0. Then you'd have to like factor off x cubed, and you would get like x squared minus 1, factor out the 2. And that would factor further into x plus 1, x minus 1. And then x minus 1 is a common factor. And then you would pull that out. That's x cubed times x plus 1 plus 2. I'm not even sure if you could actually even solve for this, but you probably don't need to, because that would be x to the 4th plus x plus 2. And I'm pretty sure that's always positive. So it means that x equals 1 would be your only solution. But that's like a lot of computation. And by the way, this can't always be done. So you'll get situations in which you can't actually solve for it, both in your homework and like if I put a problem like this on a test, I'm going to put one that you can't actually solve for. You just have to use your knowledge of what it means to be an inverse function to kind of see what the answer is. So I know f inverse of 2 really means what x value do I have to plug into the original function to get 2? And the function might be complicated, but it's going to be a value where you should be able to see it with relative ease. And I think if you look in the homework or the textbook, you'll see some examples of that. So yeah, by inspection, x equals 1. So that means your f inverse of 2 is 1. And so our derivative of the inverse function where was our f prime? 5x to the fourth minus 3x squared plus 2. So this is just going to be f prime of 1, because that's what this guy is. And that was 5x to the fourth minus 3x squared plus 2. And it's going to be 4. So this is a quarter. So the inverse function's derivative at 2 is that. Now, there are times when we want to be able to, we can't find an inverse function like for this one. Like I think in general, if you just set y equals to this guy and try to do that whole, oh, let's switch x and y and solve for x kind of thing, it's not going to work out. So we spoke about an application of derivatives, which we're actually going to, I think, talk about today again. When we were doing implicit differentiation, and we were looking at that folium of Descartes, right, this guy, where it was like impossible to solve for y. You couldn't actually solve for the y. And the idea was, though, that we could actually figure out the derivative at a certain point. We could actually figure out the points that are on this function, not by calculus means, by other means, which may include calculus actually, but there are more machinery for it in like numerical analysis. So you can find a point, you can find a derivative. That means you can construct a tangent line. And the point of the tangent line is when you zoom in, the tangent line and the function are very close. So you can actually use the tangent line to approximate the outputs of the function. So if the function itself is very complicated, like you don't even have a formula for it, what you could do is point by point, just find a bunch of tangent lines and you can approximate how the function is behaving. So here, in general, we don't really know what the inverse function is, but we can, in theory, find the derivative of the inverse at any point, which would allow us to construct tangent lines at any point, which would allow us to describe what the inverse function is doing at any point without actually knowing what the inverse function is. And so that's pretty neat, pretty useful. So we sometimes want to find the derivative of inverse functions even when we can't actually find the inverse function. Might be important. Sometimes you need to undo something that was already done. Okay, so that I think was the last example in this. So that's all we have to do with derivatives of inverse functions. Now, I was kind of in two minds about what to do next. So, I mean, technically in the syllabus, the next thing to do was to do related rates. But I think I want to do a couple of things before that. And we might not even get to related rates if I do these two things. But I think it actually flows a little nicer. Why I put related rates here is because with in-person classes, I tend to get up to this point by the time test one comes around. Well, it's happened once. Let me put it that way. I got to this point when test one came around. And so I wanted the students to have an experience of doing a word problem in test one. So test two isn't completely a shocker. And all the word problems are in the test two. So I was like, okay, let's put some word problems in test one. So that's why I kind of move related rates up this high. But technically, I wouldn't do it under normal circumstances. Yeah, and that happened once. I think every other class, test one happened like a little before I started related rates, like every time after that. But I kept holding out hope that I would somehow finish related rates before test one. Yeah. Yeah. I struggle with quiet classes, in case you didn't know. So like when the class like responds and we talk, like I can get through stuff quicker, as opposed to like, I don't know, and then I kind of pause and I ramble like what I'm doing now. Let's actually move on. I think I'm going to do linear approximation next. I think that would make more sense. And then I'm still not going to do related rates. There is stuff I could talk about that makes related rates easier, but I think, or just one important concept behind related rates, but I think while I'm giving you that concept, I'll give you other concepts as well, just because we're there. So I'll probably finish today's class doing that stuff. So it's going to be more like an information dump kind of thing. Anyway, so let's actually start. Linear approximation and differentials. So these are essentially the same thing. So you can actually just know one of them if you like. But there are some word problems where thinking of it in the differentials format can make it easier to digest. But they're essentially the same thing. I would say learning the linear approximation version is probably the nicer version to use. The other one, you can actually figure it out from that version if you have to. And I don't know how much I would test you on the other version, the differentials version anyway, but we'll see. So the idea behind this, the idea in this section is to approximate functions using a straight line. Approximate, let's say, general functions at specific points around specific points using tangent lines to the function. And that's where it comes in the phrase linear approximation. You're approximating the function with a linear function, a line, specifically the tangent line. So that's where you get the name linear approximation from. And so the idea is we have a function which may be complicated, and it may be super duper complicated in the sense that we don't even know what the function will be doing. But we can use a tangent line to approximate stuff and get away with some approximation. So let's say, I'll talk specifically about a nice application here. So let's say this is our function f of x. And I care about what the function is doing at a specific point, A. But for whatever reason, getting the definition of the function is very complicated. So trying to like examine its behavior around this point is difficult, right? Maybe I don't even know the formula for it or something. So what we can do is we can create a tangent line to the function to kind of approximate what it's doing if we zoom in, right? And so that leads us to, we want to approximate it at the point a comma f of a. Right? And, well, not really. So what we want to do is we want to approximate it for regions around this point. So we might even know what's going on at A, but we want to know if we're close to A, what's going on. So there's another point that we care about. Let's call that natural X. It's right here. Right, so there's a point X comma Y. And let's say I want to approximate what the output of the function is at that point. So there are two ways you can do this. Firstly, you can actually find the difference in the Y values between that point and the original point, right? That's called your delta Y, the change in Y values, right? So higher Y value minus lower Y value. If I know this difference, I can tell you what the output is. So if I know the output at the blue point, I can actually approximate the output at the white point if I know the difference between the Y values, right? That kind of makes sense. But not all the time will you know that. What you can notice is if I kept going, I would eventually hit the tangent line itself, right? So I would hit this function. Now that function is going to be a lot easier to understand what's going on. And it will be the thing that we can use to approximate. So that gives us another thing, right? So this is the approximation of the change in Y by using the tangent line. This is what we call dy, the differential, the guy that's in the top part of the Leibniz notation. And so we know what's going on at the blue point. Right? And we are interested in what is going on at the white point. Well, I think in the notes, the colors are inverted. I think it's going to be black. And so the idea is, maybe I should just use a different color. The idea is to use the difference in the Y value given by the tangent line to approximate can't write today, the Y value of the function. So we get the following. So in other words, we want f of x is going to be approximated by the y value for the tangent line. Now, what is the y value for the tangent line? This tangent line is passing through the point a comma f of a. So that's like your x1, y1. And its slope is going to be given by the derivative of the function. So it'll be f of a plus f prime of a times x minus a. And why is that? Well, so the point x1, y1 is like your a f of a. And we know the slope is f prime evaluated at a. And so you have y minus y1 equals m x minus x1. And so this is y minus f of a, which is the y value, equals m times x minus a, which is the x value. And then I just move that f of a to the other side. So this gives you the equation of the tangent line at that point. Okay. So what we're going to do is we're going to output the value of the function. So we're going to use this to approximate the value of the function. So this means that when x is close to a, the output of the function is going to be close, or it's assumed to be close to this expression. And this expression is very important. That is actually the main formula in this section. This is the linear approximation formula. Okay. This also leads to a formula called the linearization, but it's pretty much the same thing. I'll show you what that means. This also leads to the linearization of f of x near x equals a is given by, call this function L of x, but it's really f of a plus f prime of a times x minus a. So it's called the linearization because what we're really doing is we're essentially transforming the function into a line and using that line in place of the function. So it's called the linearization, or L of x. But these are the two important formulas. But I would probably remember this one more. So that is the linear approximation formula. So basically we're approximating the outputs of the function with the outputs of the tangent line. Now, of course, they're not always going to be exactly the same, but the idea is the closer we move here, the less and less that difference is going to be. You see, like here, the difference between the green line and the blue line isn't all that much. Of course, the farther away you move, that might change. But for now, these guys, the closer you get to that point, is the better the approximation. probably mention that. Another thing I want you to note is that f of a is the nice point, i.e., we know all the values there. So I know A, I would know f of A, and I, of course, would know f prime of A. If I didn't know these things, I wouldn't be able to actually construct a tangent line. So I know all these values. XY is the ugly point. These are not official terms, i.e., the value the point close to a f of A that we do not know f of x for, or we want to approximate it. Right? So you can always think of A as the nice x value, it's the coordinate at which we know what's going on. And x is the coordinate at which we don't know what's going on. And this has a lot of nice applications. Now, the example I'm going to do in this class is on some level going to be silly. It's going to, I think personally, it's going to be cool that we can do it, but you might not see like, okay, it's like a party trick or something. But it's actually a very important application of tangent lines and derivatives. It's one of the most important applications of tangent lines and derivatives, being able to do this. And we do this all the time. So for example, and we do this in some crazy situations. So for example, we can have like the date here and like a stock price, for example. Right? One of many models, right? So you have the stock price is a crazy function, right? We don't even know what it's doing at any time, but we know what's going on at, say, this point right here. Right? So let this be a comma f of a. Now, we have no idea what this function is, a formula for it, nothing. But let's say this here is the present. Now, how do you make money is you need to know the future, essentially. And if the stock price goes up, what you want to do is you want to buy it now and then sell it later when it's worth more. If the stock price goes down, what you want to do is you want to short the stock. So whether the stock is going up or down and you making a bet on that is what's going to make or lose you money. So the thing is, though, the thing is unpredictable. You don't know what it's going to do in the future. However, extreme changes usually don't happen. At least they don't happen in very small time windows. So let's say you are at the present here. Right? So that's at time x equals a. And there's a point here in the future. At point x. Now, you don't know what that is. It could go up, it could go down, could go straight. Like, we don't know where it's going to be. What we could do, however, is we could construct a tangent line here. And then what we do is we pretend that whatever that coordinate is where the stock price is going to be in the future. And what we want to do is we want to make this a very small window. Because the smaller the window, the more accurate your approximation. Say 1/10,000th of a second. Now, I don't know what's going to happen tomorrow. I don't know what's going to happen an hour from now. But in the next 1/10,000th of a second, it's not really going to make that much difference. There is going to be a difference, but it's going to be very small. However, what I can do is I can use the tangent line to guess what that point is going to be. So I could have my computer construct a tangent line and predict where the output is going to be a millisecond from now. And for a human doing something like that, that's actually not going to give you a lot of much advantage. Like, what are you going to do in a millisecond, right? However, if you're a supercomputer and you can do billions of things in 1 second, 1/10,000th of a second is forever, right? You can buy and sell thousands of stocks in that time period, right? So the difference in the price in the next millisecond is going to be a matter of cents. However, you get that right enough millions of times, thousands of times in that 1 second, that kind of adds up to a lot of change, a huge chunk of change, right? And so you can actually use a tangent line to predict what the function is going to do, even when the function doesn't exist. You're predicting something in the future. And yeah, it's one way in which banks can make money off of this. It works, right? This is one of the ways that you could do it. You can guess what the function is going to do using derivatives. And yeah, a person won't be able to take advantage of that because any time window in which a person can take advantage, it's too long. It's not a good predictor anymore. Because the farther away you get from the function, the less accurate you would get in theory. So, but if you're in a very small window, the prediction is going to be, in theory, more and more accurate. And in practice, it ends up being pretty accurate. Now, you're not going to be spot on, but the difference between the actual price and what you guess the price is going to be very small. So even if you lose a little bit of money, you're going to gain more because you have the prediction. And so, yeah, you can have a very fast supercomputer kind of guess, approximate the coordinate, approximate what a tangent line to the coordinate would look like, and then approximate some future point at a very small window in the future and buy or sell the stock automatically based on what that future guess is. And yeah, you're Goldman Sachs or someone else. So there are some really cool applications for what I'm showing you. But in a Calc 1 class, we're not really going to do the cool applications. We're kind of going to do the kinds of applications that we expect students at a Calc 1 class could do by hand. So that's what we're going to do. But yeah, linear approximation, super duper important application of derivatives. One of the main things we use derivatives for, because we use it to help us predict what's going to happen. Because unless there's like a natural disaster, any function that we're tracking in nature, it usually doesn't spike up to infinity in like a matter of that, right? Things don't actually change much from 1 second to the next. They can change a lot over a lot of time, but from like one moment to the next, it's going to be relatively close to what it was doing before. But you can't really predict, is it going to go up or down, sideways? You don't know. But whatever it does, it's not going to be super far off from what it was doing a moment ago. And so using that idea, we can do something like this, construct tangent lines. So very cool application. We're not going to do anything that cool, though. We are going to do something like approximate a certain value, which you could actually calculate, but we're going to do it by hand, and it's going to be really cool how close we can get. So here are the examples. One, I might say, use linear approximation or differentials to approximate the value of, and let's say it's the square root of 3.99, right? Which, yes, I know you can do this in a calculator. That's not the point. Sorry, my headphones are connected to my phone and someone was calling me. So yeah, I know you can do this in a calculator. That's not the point. The point is I'm going to show you that I can do it without a calculator and get it pretty accurate, right? And the reason is because I know what the square root of 4 is, which is super close to 3.99. So I can actually make an accurate prediction, or a pretty good prediction, using tangent lines, which I can compute easier. So when you want to do something like this, step one, we want to be able to use this theory. So what we're going to do is we're going to set up a function. So you're going to set up your function, f of x. So f of x, I want to use this function to approximate the square root of 3.99. Now, you just have to come up with a function that you think would be a good candidate for doing that. Since I want to approximate the square root of something, square root of x seems like a really nice function to do. So set f of x equals the square root of x. And just note, we want to approximate this. We want to approximate f of 3.99, right? So the first thing you do is set up a function. Second thing you're going to do is you're going to find your a and x. So remember, a is the nice value. Nice value. And this is the ugly value. Right? Now, the ugly value is going to be the value that we don't know anything about, which the whole point of this problem is to figure out what is the square root of 3.99. So x equals 3.99 is going to be the value that I don't know anything about. Now, a is a value that has to be close to this value, which I do know all the information about. In this case, 4 seems like a very good candidate, right? So this here is the value we care about. And then what we do is pick a value super close to it. Pick a value close to it. For which we know all the important values. Okay. So I have the function square root of x. I want to approximate it at 3.99. I don't know what it is at 3.99, but I do know what it is at 4, and 4 is super close to 3.99. So what I'm going to do is I'm going to use a linear approximation based at 4 to guess what's going to happen at 3.99. So the third thing we're going to want to do is to actually find the approximation values. So we're going to find f of a and f prime of a to use in our formula. So here we know that f of x equals the square root of x. This means that f of a equals f of 4, which is just the square root of 4, which is 2. F prime of a, f prime of x is 1 over 2 rad x. This means that f prime of a is f prime at 4. F prime at 4 is 1 over 2 rad 4. So that's a quarter. Then finally, what you're going to do is plug into linear approximation formula to make the estimate. So we know that f of x is approximately equal to f of a plus f prime of a evaluated at x minus a. This means that 3.99, which is f of 3.99, is going to be approximately equal to f of 4 plus f prime of 4 times 3.99 minus 4. So this here is my a, this is my x minus a. This is the x. I care about f of x. And so this is going to be f of 4, which is 2, plus a quarter. And 3.99 minus 4, that's going to be minus 0.01. So that's going to be minus 1 over 400. 2 is 800 over 400, so this is 799 over 400. And that's my approximation. Yeah, so that's what I think the square root of 3.99 is. Now, for fun, let's check. If I take 799 out of 400, that is, it actually terminates. It's 1.9975. Okay. Now, if I take the square root of 3.99 and use my calculator, this is a non-repeating decimal. It's going to go on forever, but let's see what the first few values are. 1 point, drum roll, 9. That kind of made sense because it's going to be, it should be close to 2. 9. All right, that's yeah, okay. But there's no way the next number is a 7. 7. The next number was actually a 7, and the next number 4. Oh, we didn't make it. However, the next number was a 9. So if I rounded, I would be correct to 4 decimal places. So here, this is the estimate. And it's correct to 4 decimal places. With rounding. Right? Which is crazy. I can take this crazy number and me, a lowly human by hand, I could know what the answer is up to 4 decimal places without a calculator. So it's pretty cool. At least I think. Now, no one would ever actually do this, but this is Calculus 1. We can't do all the fun applications here. We have to do these kind of silly Mickey Mouse ones. So 2, I'm going to ask you to do this again, but with a different function. And you can maybe try it over the break. Use linear approximation to estimate what I want, the cube root of 8.01. And we will do that when we return after these commercials. Let's take a break here. It's a little before 7:30, but I don't want to start the next problem and go push too far beyond 7:30. So we will stop here and take 10 to 12 minutes, maybe like 7:40 we can come back. Yeah, so let's actually do that. Let's take a break right here. And I will see you guys in like 10-ish minutes or so.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. The show will start in 6 minutes. The show will start in 5 minutes. The show will start in 4 minutes. The show will start in 3 minutes. The show will start in 2 minutes. The show will start in 1 minute. And now, on with the show.
All right, we're back. Let's actually look at this problem. Something in the chat here. All right, so use linear approximation to estimate this, and I kind of wrote that in the line, I don't know. It's okay. Did anyone try it and get an answer or no? Just enough time to stretch your legs. Well, let's run through it one time, see where we can get here. So the thing is, we're going to set up a function. So f of x equals the cube root of x. 2, choose x and a. Here you're going to have your a and your x. Your x is going to be the guy you want to approximate at, so that's 8.01. Your a is going to be something super close to that, which is a nice value that you can kind of know what it is, and that would be 8. So yeah, we know the cube root of 8. That's just 2. It's easy. 3, you're going to find f of a and f prime of a. So we know that f of x is equal to the cube root of x is equal to x to the 1/3. This means that f of a equals f of 8, which is 8 to the 1/3, which is again 2. And f prime of x would be 1/3 x to the minus 2/3. So that would be 1/3 times the cube root of x squared. So this means f prime of a is f prime of 8. It's going to be 1/3 times the cube root of 8 squared. Cube root of 8 is 2, 2 squared is 4, 3 times 4 is 12, so that's 1/12. And 4, I want to plug in. So we know that the cube root of 8.01 is equal to f evaluated at 8.01, which is approximately f evaluated at 8 plus f prime evaluated at 8 plus x minus a. So that was 2. This was 1/12. This is 0.01. So this is 2 plus 1 over 1200. And 2 would be 2400 over 1200. So this is 2401 over 1200. And that's your answer. For fun, let's check. If you do 2401 over 1200, that's actually equal to 2.0008333, and it kind of repeats after that, which you might recall is 3 bar with a bar on top to say that, oh, the 3 just repeats after this. If we actually take the cube root of 8.01 from calculator, it's going to be 2.0008. Good up to 4 decimal places. 3, good up to 5 decimal places. 298. Oh, okay. So, however, with rounding, 6 decimal places by hand, like I didn't use a calculator. Right? So you can imagine this is what the actual stock price was. This is what the supercomputer would guess it is. You're still right up to 6 decimal places. Like you're going to make money if you place the right bet. So yeah, you lose whatever money is not accounted for down here, but you still make all of this, which is the bulk of it. Yeah. So that's linear approximation. Look, no hands. That's kind of where the Calc 1 stuff where it brings us. But really, there are a lot of cool applications to this thing. Here's an example again. 3. Yes. Find the linearization of f of x equals sine of x at x equals pi over 6. So the linearization really is just, remember, it's the linear approximation formula. It's just another way we want to express it. Right? It's pretty much saying the y of the tangent line is this. We call it big L in this context. It's called a linearization, but it's still the same linear approximation formula. So here, f of x equals sine x and a equals pi over 6. So this would mean that f prime would be equal to cosine. And so the linearization is going to be f evaluated at a plus f prime evaluated at a times x minus a. So f of a, this is just going to be sine of pi over 6. F prime of a is going to be cosine of pi over 6. It's going to be x minus pi over 6. Sine of pi over 6 So it knows a half. Cosine pi over 6 is radical 3 over 2. So that's your linearization. This is pretty much the equation of the tangent line at the point. X equals pi over 6. Yeah, so linearization isn't a big difference. So let's look at differentials. Now, you can take a whole class in differentials, but we are not going to need to go that deep. We're pretty much going to examine how we can think of the differential in this case. So it's a similar idea to the above, but different notation. So given, say, y equals f of x, of course, you would know that dy dx is equal to f prime of x dx, f prime of x. And so we can solve for dy, that's f prime of x dx. So now this is called the differential of y. It's meant to approximate the change in y. Meant to approximate the change in y, which is your delta y. So this is what your, how much your y value is going to change from the point where you know everything to the point where you don't. And it turns out you can actually get it from this thing. This is the differential of x. Now, that is technically an approximation of delta x, but they're actually always the same. Your dx is actually going to be delta x. The reason is it's your independent variable. You're going to know what x value you're plugging in. You're going to know what you want to approximate. But your dy is only approximately equal to delta y. And the idea is you have your function and you have, say, the tangent line here. And you start here and you care about here. So this here is your change in x, but that's actually going to be your dx as well. Like you know exactly what it is. You know what x value you care about. So your dx approximation is just going to be your delta x. Like you know exactly what it is. That's the best approximation you can get. However, the change in your y value is in general not the same as the change in the value given by the derivative, the tangent line approximation. So the idea is when these guys are close, your dy is close to your delta y, but they're not exactly the same. But your dx is always going to be your delta x. And so with this idea in mind, to calculate the new y value that we care about, what you can do is you can start with the old y value and add the change in y. So you can start with the new y value is going to be your old y value plus whatever change happens. Right? So the y value was 1, and then later on it's 3. The change in y was 2. You can so you can get from 1 to 3 by taking 1 plus 2, right? Now we don't always know what this is. So what we can do is we can approximate it with the old y value plus dy. Now the dy, the old y value is of course going to be f of x plus the dy I just showed you was f prime of x dx. Or let's say, just to match it up with the notation, let's put a and a here. So this is the old y value at the point, and it's going to be that at the new point. Your delta x, remember, is exactly the same as your change in x. This is equal to your delta x, and that's equal to x minus a, right? It's the new value minus old value. Right? That's how you can represent change. If the new value is larger, you know you move to the right. That was a positive change. If the new value is smaller, you'll get a negative change. You'll move to the left. But essentially, you'll see what that is that this guy is just like your f at x, whereas this guy is again your f of a. This guy is your f prime of a, and this guy is your x minus a. So it's pretty much the same thing, except you're using like dx and dy to represent the change. But you can actually derive one thing from the other. So yeah, the differential is these dy's and dx's. They're called differentials. Now, what they actually do and how they actually function, we're not going to go too deep into that in Calc 1. But for us, we can just think of them as their approximations for the change in the y value and the change in the x value, respectively. And the idea is you want a change in one value. You take the derivative of the function, multiply by the change in the independent variable. That's the idea that we want to actually take further. So with that idea, you can do certain word problems. So this is example 4. So here is one.
Find the relative error in computing. Okay, so here's a word problem, which I guess you can like take a snapshot or write it down if you want. So we're going to do this one. And then I think I want to talk about some properties of the derivative, I think. Okay, so again, not a super interesting application, but just to kind of give you a simple application to understand what's going on. So we're measuring the dimensions of a cylinder, but they sent Frank. Frank forgot his glasses. So Frank is I think it's 20 centimeters for this one and 10 centimeters for that one. So he can't see properly, right? So Frank is off. He's off by something. We don't know how much, but whatever he says, it's definitely not it because he forgot his glasses. So let's say we estimate Frank can be wrong by up to, like 1%, which is being generous to Frank because you know how Frank is. So we might say, all right, he might make an error of 0.01. So it can be up to 20.01 or 19.99 or something like that. Like the fluctuation between the actual value of the radius, it would be that, right? And you have the same kind of thing for the height, right? So we know like what the basic measurement should be, but we also know the possible change in each measurement. So the idea is that change in something, whenever you have a small change in something, like a small error, you can think of those as the differentials, right? Just like how dy is the change in y, dx is the change in x, you can have all these differentials. So here, we can let v equals volume, r equals radius, h equals height, and all of those imply that dv is a change in volume. dr is a change in radius. dh is the change in height. Right, the small change. You could look at this in this context as like the error, right? So it's a small change. Right, you never use the dx and dy and d anything to represent some big change. It's always a very small change because the tangent line and the function behave very similarly when you get super close. So yeah, so we have that. So now what we want is find the max error in computing the volume. Right, so what we would do here, so this also means that I know R, I know H, I know dr, I know dh. R is supposed to be 20, H is supposed to be 10, but they each have a possible error of 0.01. And so A, the error in the volume would be dv. Now, v equals, remember that this is pi r squared h. So you're going to go through, you're going to take derivatives. You can look at this as implicit differentiation, or you can look at it as this expression here, where you take the derivative of the thing times the change in the independent variable at that point. So what we would do here is that dv would be, you have two functions here, so you need the product rule. So it's 2 pi r dr plus pi r squared times 1 dh, right? You can think of this, if you want, as like, oh, this was dv dx or dv dt or whatever, and then you multiply it all sides by dx. You can also think of it that way, and that would make sense too. But right here, that's how you'd apply differentials. So you find the derivative with respect to r, find the change in r, you find the derivative with respect to h, you find the change in h, and you attach them this way because that's how differentials work. And so now, what that means is that the change in volume is going to be 2 pi r, I know is 20, dr is 0.01. R I know is 20, dh is 0.01. So the change in volume, I think, wait, I'm missing something. I'm missing the h here. All right, differentiate the r, the h has to stay. And I left the pi r squared there too, okay. H was 10. Okay, so I think 10 is going to cancel one of those 10s because that's 1 over 100, and then this part is going to cancel all of that. So then that's just 4 pi in this case. 20 squared is 400. So that gives you another 4 pi. That gives you 8 pi, is the approximate error in the volume. So if you send Frank over, he came back and told you what the measurements are, but you assume that he's 1% wrong in all his measurements that he gave you. How much could he be wrong by overall about what the volume is? He can be wrong by 8 pi cubic units. I tend to not care too much about units in this class. Like if you're in your chem class or your physics class, yes, the units are very important, but I don't particularly care too much about them. So that's an example. If you want, what was the other thing? So the relative error is whatever the change in error is out of the total volume. It's kind of like you're finding a percentage error. So B relative, this means like proportional percentage, etc. error. So the relative error is going to be essentially dV over V. Like how wrong were we out of the total volume? So this is going to be 8 pi divided by, the actual volume was pi r squared times h. So essentially we have 8 pi, the pi's cancel, and we have 4,000, right? So this is if you wanted to kind of have an idea. Okay, so I know we're off by 8 pi, but is that a large difference or a small difference? It's actually not that big. It's like a 0.002, or it's like 0.2% error. Yeah, and that's that. So problem like this is probably what you definitely need to know. Problems like this, because I'll ask you about that. Problems like the others, like just find the linearization of something, probably won't ask that, but you can make that. You'll see some of that in the homework. Finding, and these word problems, yeah, I might throw something on like here, but might also not, depends on my mood. Actually, I already wrote the second test a long time ago. I don't even remember now if I put this on. Okay. Okay. So let's talk about something else. And for the most part, I just want to do some information dump and kind of tell you about some general facts about the derivative. Here are more facts about the derivative. And then we can go into the applications part. Is there any other let me just make sure that there are no more like calculation stuff that I want to do, because I would just get that out of the way. No, linear approximation was the next thing. And then I wanted related rates. Okay, yeah. So like there's only one extra fact about the derivative that is probably obvious, but I never really explicitly said it, that you need to know for related rates. Yeah, that you would need to know for related rates, but I never actually explicitly said it. So I want to say it now. And while I'm saying that, I might as well tell you some other things about the derivative, I think, which will come in handy later. So let's do more facts about the derivative. Wait, there's more. I was writing a lot smaller earlier, then I started writing bigger. Okay, whatever. Okay, so here are some more facts about the derivative. This thing we know and love, the thing that helps us to solve the rate problem. So back to interpretations. So we know that f is a differentiable function and f prime is its derivative. How can you interpret the derivative? Recall that some interpretations of the derivative. It is the slope of the tangent line to f at x. We could also think of this as the slope of the curve. So maybe I should do. So I do want you to think of it. So this is the derivative of f of x. But I do want you to understand that derivative and slope, they're the same. They're the same, right? You can think of these as synonyms. It's just that derivative is more general. So slope we kind of use when we're only talking about straight lines, but the derivative really is slope. It's just a generalized form of slope. So I want you to remember that. So whenever you hear about the slope of something, chances are you want to do the derivative. Another thing that this is called, it's called the instantaneous rate of change. As opposed to the average rate of change, which is over a large window, we want the change at this point, and the tangent line is what gives us that. Another way you can think of it is how fast y equals f of x is changing in relation to x. So remember the example that we did to kind of introduce the idea of the derivative was, oh, we were going 50 miles per hour, right? And what does it mean to go 50 miles per hour? It means that the mileage changes 50 times faster than the time, right? So every time the time moves forward by 1 hour, the mileage would move forward by 50, right? And so after 2 hours, you'd be 100 miles away. After 3 hours, you'd be 150 miles away, because the mileage is changing 50 times faster than the time, right? You want to know how many miles you traveled, just multiply the hours by 3. And so that is going to give you the proportion, right? And the slope was what gave us that. So this would gives a formula for the above. Right. So if you want to interpret it as any of these things and you want a formula for any of these things, you can use the derivative to get a formula. So that's what a derivative is interpreted as, some of the main interpretations that I want you to remember. But now we're going to go further. We're going to interpret some other things about the derivative and what the derivative can tell us about functions. So let's move forward with that. Interpretations of the sign of the derivative. And by sign of the derivative, I literally mean the sign, whether it's positive or negative. So I don't know, maybe I should turn that on because I'm going to do a lot of writing now. So here, I'll somewhat be doing like an information dump. So we're just going to be learning some new things, not necessarily doing any calculations right now, but I want you to understand some very important concepts that will come in handy later. So go with some examples. I think I want 4 of them. So these are, X and Y axes, right? So let's say I have a straight line like this versus straight line like that, parallel to the X axis, versus a straight line like this, versus a vertical line. So vertical, horizontal, and slanted, right? So here, you would know that we know that M, the slope, we know that M in this case is greater than 0. It moves up as you go from left to right. So this guy here is, of course, the slope, which is a synonym for derivative. So this essentially would say f prime would be greater than 0 in such a case. So similarly here, so you can say the derivative is greater than 0. Similarly to here, you can say, well, m equals 0 here, but that's just talking about slope, which we know is talking about derivative, which we know is just saying f prime equals 0. Over here, our m is negative. That means we're talking about the slope being negative, but that really means that the derivative is negative because the derivative is the slope. So we can express that as f prime less than 0 the whole time. In a vertical line, we have no slope, right? Undefined, which means the derivative is undefined. Right? So because, remember, the derivative is helping us find the slope of a tangent line, so its sign can be interpreted the same way we'd interpret slope. If the sign is positive, what you can interpret that as it's moving up as you go from left to right. Sign is negative, it's moving down as you go from left to right. If the slope is 0, it means it's horizontal. If something is vertical, then it has no slope. There's no concept of slope in that case. So this leads to the following notion. Let I be some interval around x. Then, and let f of x be differentiable on I. Then it turns out that f of x is increasing on I if and only if f prime of x is greater than 0 on I. So the notion of increasing can be attributed to having positive derivative. So whenever your derivative is positive for a function, you can actually interpret this as to mean the function is moving up as we go from left to right. I don't know what exactly it's doing. It might not be a straight line, but whatever it's doing, it's getting higher. The output is getting higher as the x values get higher, or as the inputs get higher. So that would be an interpretation of the sign. If f of x is decreasing on I, if and only if, that would mean that the derivative is negative on I. So decreasing, you would think associate with negative slope, right? So of course, if the slope is 0, you don't think of it as increasing or decreasing. But there are problems with me just saying f prime equals 0 means it's not increasing or decreasing, which we'll see later. But for now, you can actually just assume these two are true. If I can actually find the derivative at the point on this interval, then wherever the derivative is positive, it will be an increasing function. Wherever the derivative is negative, it will be a decreasing function. So knowing that increasing and decreasing can be interpreted as the sign of a derivative is going to be a very useful thing. Now, what I want to talk about is higher derivatives and their application. Applications, properties. Okay, so it turns out that sometimes, not all the time, but a lot of the time, with a lot of the functions that you'll see in Calc 1 anyway, those functions are very nice. You can actually take the derivative of a function multiple times. So you can take the derivative of a function, and then whatever the answer is, you can take the derivative of that. And then whatever that answer is, you can take the derivative of that, the derivative of that, derivative of that. And it's like Russian dolls going all the way down. You can take derivatives multiple times, sometimes. And it turns out that these derivatives are called higher derivatives. So if you take a derivative, in this context, we will call it the first derivative. And if you take a derivative of that derivative, you say you found the second derivative. And you can find the third derivative and the fourth derivative, etc. And these guys will have, they have meaning. And for us especially, we will want to give meanings to the first two derivatives especially. The third derivative, not so much. Well, not at all, to be fair. You might care about the third derivative in like a physics class or something. So yeah, that's basically the idea. Sometimes we can take the derivative of a function more than once. So you can have your function And then you can find the derivative. And then what you can do is you can find what's called, so this would be the first derivative. You can find what's called the second derivative. And then you can find what's called the third derivative. And these are just the derivatives of the previous thing. So this is the derivative of the function. Here, this is the derivative of the derivative. Here, this is the derivative of the second derivative, etc. And you can just keep going. Not all the time, but sometimes you can actually keep doing this and, you know, ... You can keep going. And it turns out that being able to do this is useful. So these derivatives, second, we call them higher derivatives. These higher derivatives and by that, I'm referring to things like the second derivative, third derivative, etc. They have various applications. Which we'll get to, but first let's talk about notation. Okay, so first notation. How do we actually write these guys down? So let me show you the prime notation. So this is Newton's prime notation. Show you the Leibniz notation. And talk about the derivative there at. Okay, so we already know the notation for the first derivative, right? So this is f prime of x, and this would be dy dx, right? And this is the first derivative. Or just derivative. However, and actually, I might want to actually talk about the other function first. Because that'll be a concept that we're going to, well, you'll use it in Calc 2 and other classes. So here's the original function. And this is just called y. And this is, we can think of it as the 0th derivative. Right? Like you haven't taken a derivative, you've taken 0 derivatives. That is the original function. Right, that's the 0th derivative. But then you can take the first derivative, which means you take the derivative, which means you do limit as h approaches 0 of f of x plus h minus f of x all over h. Sometimes you might have a nice formula for that, and you can put it in here. And that would be the notation. How do you do the second derivative? Well, Newton just put another prime on it. So it's called f double prime. Leibniz here, he puts a power on it like this, because here it's like, so this is f double prime. And really it's like you take f prime and then you take a prime of that. And we just do that. For Leibniz, what he had was you have the derivative of a function, and then you take the derivative of that. So your d and the d gives you d squared, and the dx times the dx gives you dx squared. And so that's how you can get these kinds of notations. So this guy's called the second derivative. Okay. Now you can also have, of course, the third derivative. And so on, right? So you can have like a first derivative, the zeroth derivative, which is the original function, the first derivative, you have the second derivative, you have the third derivative, or f triple prime, and you can keep going. So let me just dot, 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 dot. Let's say you get to the 17th derivative, and no one's going to sit there writing 17. Once you pass 4, you don't do primes anymore. You do this thing where you put the derivative as a number in the power. So you put parentheses around the power. So again, be careful with notation. If you have a power with parentheses around it, it actually means a derivative. So this would be d17y over dx17. This is the 17th derivative. Which, yeah, we're definitely not going to do an interpretation there. But the idea is eventually you get down way, way down, and you can keep going usually. So at least in Calc 1. So you'd write this as f to the n of x. And this is dny, dx to the n. This is the nth derivative. Right. So you can have the third, fourth, fifth, sixth, seventh, eighth. There are functions, of course. Pretty much every function you've seen so far is differentiable forever. You can just keep taking derivatives forever. And functions like that are actually really nice. We can do a lot of cool things with them in Calc 2, which you can just wait for Calc 2 to figure out what we can do with that. But functions that we can differentiate forever that also have one other special property, you can do things like create Taylor series for them, which is super cool and super useful. But that's the notation. That's how we do first and second derivative. So of course, this is assuming the derivatives exist. Right. Because it's possible for a function to not be differentiable. We saw a case like that with absolute value of x. It's also possible that you can differentiate a function once or twice, but then you can never do it more times. You have all sorts of functions that you can differentiate one time, but you can't do it anymore. You can differentiate 2 times, but you can't do it anymore. You can differentiate 3 times, but you can't do it anymore. There are functions like that. So don't just take it for granted that, oh, we can always calculate the derivative. It's not that straightforward. Life is more complicated. So for us, the second derivative is going to be the most important higher derivative. Okay. And let's look at let's focus on the second derivative now. We know a lot about the first derivative. We've spent a while on the first derivative. We know how to calculate it in various forms. We know its definition. We know how to use it implicitly, explicitly. We know a lot of stuff about the first derivative. So let's have the second derivative have its 15 minutes. Right. So the second derivative, remember this is the derivative of the derivative. You can also think of it as the slope of the derivative. Right? So the derivative is just another function. And then if you find a derivative again, what you're doing is you're finding the slope of this new function. So you're kind of like finding the slope of the original function. Which at first might seem like it wouldn't make any sense, but it actually makes sense. Maybe I'll talk about what that is. Here are some important applications. For us, there are two important applications. One is the physics of motion. And this is to say that t equals time. If s of t, this is the position function, gives you the position at time t. Then if you take the derivative of that, that gives you a new function called v of t, that gives you the velocity, right? Which we kind of knew about. That's the speed in a particular direction. But you could take the second derivative, usually, and that would give you a function that we call a of t, which is the acceleration. Now, these functions tell you different things. So this one is like position, right? Like, where are you? Now you can find the rate of change of position, which is velocity. So this is answering the question, how fast are you moving? Right? But you can also ask another question. You can go higher, get even more meta. So you can ask, what's your speed? And they can tell you, oh, this is my speed. Oh, so that's how fast your position is changing. How fast is your speed changing? That's like asking, are you speeding up or slowing down? Is your current speed making a positive change or a negative change, right? So this is like, are you speeding up or slowing down? And these are all kind of like instantaneous. So someone can come and say, where are you right now, right? The position function will tell you that. Okay, how fast are you moving right now? The derivative will tell you that, the velocity function. Okay, are you right at this moment, are you getting faster or are you getting slower? The second derivative would tell you about that. So these are some important applications. So these are all rates of change of the previous guy. So you have rates of change. You can actually keep doing that. In a lot of physics classes, the third derivative is also going to be important. And the second derivative is called acceleration. The third derivative, so the first derivative is called velocity. The second derivative is called acceleration. The third derivative is called jerk, right? So if someone calls you a third derivative, now you know what they're actually saying. I've seen T-shirts like this, and I don't know if people know what it means. But you'd see people with T-shirts like, you are a third derivative, and they'd write like F triple prime on the T-shirt. And it's like, okay, I guess this math dude is like, no, he's calling you all jerks. So the third derivative is called a direct, but we don't care about that. We only care about the second derivative. So that's one application. Another application is the idea of concavity, it's called. And there are two kinds of concavity. You can be concave up and concave down. Okay, so let's talk about one at a time. Concave up. What does it mean to be concave up? We say f of x is concave up on I if f, or I already mentioned f as a subject of the sentence, if it always lies above its tangent lines on I. So you'd have your function f. You can have a function like this. If every time you pick create a tangent line, the function is on top of that tangent line, you would say that the function is concave up there. It's always up above the derivative. It's always up above the thing. So it's called concave up. Note what's happening to the slopes here. Note the slopes are increasing, right? So you might have a tangent line here. The tangent is zero, the slope is zero. But notice that it's getting more and more positive. It's getting steeper as I go up. So it's getting higher and higher positive numbers. It's like saying the slope is increasing. So what does it mean for the slope to increase? Well, what does it mean for a function to increase? We talked about that earlier. A function increasing means that its derivative is positive. So if the slopes are increasing, it means that the derivative of the slopes are positive. So this means, well, the derivative of that is positive, and so that means the second derivative is positive. So a function will have this behavior when the second derivative is positive. So that would mean f is concave up on I if and only if the second derivative is positive on I. So anytime your second derivative is positive, you say your function is concave up. Now, what is concave up? As you can see, any function that kind of has this behavior would naturally shape like a smiley face. So concave up is like a shape. So what kind of shape? There's a mnemonic, concave up, like a cup. So concave up, you're shaped like a cup, like you can hold liquid. Or you can think of it as up, you're happy, you're positive, you're smiling, second derivative is positive. Smiley face, it shapes like a smiley face. That's what it means, right? So this is just a math way of saying, oh, it looks like a smiley face. To say that, you say concave up, right? So do not think that it means increasing. You can do both, right? So you can have a function that does this. You can also have a function that does that. So this is concave up. I'm going to call it CU from now on. And increasing. And this is concave up and decreasing. Concavity talks about shape, not increasing or decreasing. you can be doing either one and be concave up. Similarly, concave down is, of course, the other one, kind of the opposite of a smiley face. What if it means a frowny face? So we can say F is concave down on I. If it always lies below its tangent lines. On I. So it's down on that, right? So that is concave down. So it pretty much means your function would have to look like this for that. You'll notice that the tangent lines are always on top of the function. Another thing you'll notice about the tangent lines is that their slope is decreasing. Here it was a very positive slope. Now it's like zero slope. You went from a positive number to zero. You're actually decreasing. So this gives you the criteria for concave down. Note, slopes are increasing. And what that means is the derivative of the slope. And remember, slope is just a synonym for derivative. So this is like saying the derivative of the derivative is increasing, is positive. Is, I meant to say the complete opposite, are decreasing. So the slopes are negative. So this is saying that if I take the derivative of the derivative, which is the second derivative, I would get less than zero. And so this leads to F is concave down on I if and only if the second derivative is negative there. So again, concavity is talking about shape. You'll notice that any guy that looks like this will kind of shape like a frowny face. It's the opposite of a smile. So the mnemonic is concave down like a frown. Right? So you're down, you're negative, you're sad, you're doing the opposite of smiling. And again, you can be doing that in increasing, or you can be doing that in decreasing. So this is concave down and increasing. And this is concave down and decreasing. Right? So do not mix this up with increasing or decreasing. The first derivative tells you about that. It's worth mentioning again. Concavity is about shape, not whether a function is increasing or decreasing. But rather its shape as it does so. So concavity is about shape. Essentially, you kind of want to describe, do you shape like a frowny face or a smiley face, essentially. And you can be moving up or down as you do this. So concave up means you're like this. or this concave up like a cup. So this here is increasing. This here is decreasing. And we have concave down. Will look like this or this. And this is when it's increasing. This is when it's decreasing. And you have the mnemonic concave down like a frown. I think I'll stop here. I want to tell you about inflection points next time. And yeah, I'll probably keep this in the same notes, just continue with this here. But yeah, so it turns out with concavity, you can talk about this property called inflection, which is pretty much when you switch a concavity. So it's when a function switches from a smiley face shape to a frowny face shape, or vice versa. And that's actually important for a lot of reasons, figuring out when a function does that. And next time I'll talk about that. I'll talk about inflections, how we can interpret them. And I'll also talk about specific mathematical ways of determining concavity, like by calculation, and where to find inflection points. I'll give you guys that next time. But for now, we'll stop there. And yeah. So thank you for your time and attention, but that's it. It's about that time. Have a good night, everybody. And I will, I think that's it. So I will see you guys in the next one.